These are the notes for AP Calculus on the topic of the average value of a function on an interval. So, when you first think of average, let's think about how we'd find the average of a set of numbers. Well, you would take those numbers, add them all up, and divide by how many numbers there are. However, if you want the average value of a function on some interval from a to b, in this case, to make this simpler, let's make a the x-intercept right there, and let's make b the x-intercept of this function right here. So here's our graph of f of x. Well, if we want the average y value of this function on this interval, on average what it is, we'd have to add up, if we use that same technique, we'd have to add up every single y value here, and there's an infinite number of them, and divide by infinity, how many there are. Well, that doesn't really work in practice. But with calculus, we can actually find the average value without too much difficulty. So let's see where we get the formula for the average value. Well, we can see the average value would have to be the lowest y value here is 0, and the highest it gets is 4. So it'd have to be somewhere between 0 and 4. So choose somewhere where you think the average value of this function is. I'm going to just pick right there, and label that as the average value. And then wherever you chose your average values, take your ruler and draw a horizontal line across on that interval from a to b. And then draw the rectangle down from that average value. So if we pick the correct average value there, mine's probably not exactly right, then what would be true is the area of this rectangle would equal the area under the curve of f of x from a to b, if it's the right average value. So let's write that down over here. So the area of that rectangle would equal the area under f of x on the interval from a to b. Well, the area of the rectangle is base times height. Well, to get the base of the rectangle, notice you can just go b minus a would give you how far that distance is. And to get the height, well, the height is just the average value, whatever that actually is. And the area under the curve f of x on the interval from a to b, well, remember the exact area comes from the definite integral from a to b of our function f of x, gives us the exact area. So, since that's true, if we want a formula for the average value, all you'd have to do to isolate the average value is divide by b minus a. So then the b minus a's would reduce out. And since b minus a, those are just constants, those can be pulled out in the front, and they're on the denominator, so 1 over b minus a. Goes out in the front. And then the integral from a to b of f of x dx. There's our average value formula. And this works as long as it's a continuous interval from a to b. Otherwise, we couldn't get the area under the curve if it's not continuous. So another way of thinking about why this is we're just taking the area under the curve and dividing it by the width, essentially, which gives you the average height, which is represented by this rectangle. All right, let's see how this formula works on some example problems. We want the average value of this function on the given interval from -1 to 2. That's like our a and b. We'd start off with 1 over b minus a, in this case 2 minus -1, times the integral from -1 to 2 from a to b of whatever you want the average of goes right here. In this case, it's this function f of x, so 3x squared minus 5 times dx. And this simplifies to be 1 over 3. So we're really just dividing by the width of the interval, which is 3 in the end. And then this one doesn't require u substitution when to integrate because there's no function inside and these are just subtracted. We can integrate each one separately. So when you integrate the 3x, you get 3 stays out in front, and then x cubed over 3, minus, when you integrate 5, you get 5x. And this is evaluated from -1 to 2. You can see it simplifies a little bit. The 3's reduce out. So we have 1/3 on the outside. And then when you substitute in 2, 2 cubed gives you 8. And then 2 times -5, -10. And then minus, when you substitute -1 cubed, it's -1. And then -1 times -5 is +5. We keep simplifying that. We get 1/3. So 1/3 is times this whole thing. 8 minus 10, -2, minus -1 plus 5 is 4, which gives you 1/3 times -6. And that just simplifies to be -2. So that's the average value of this function on the interval from -1 to 2. Well, let's think. Does that make sense that we have a negative average value? To see if it does, let's think about what the graph of this looks like. Well, if you recognize this graph, you can see that would just be a parabola. Right? So let's just do a rough sketch of what that would look like. So it'd be a parabola that opens up because the a value in front of the x squared, the coefficient is positive. This -5 would shift it down 5 units. So the vertex would be right here at 0, -5. And then we're only looking on the interval from -1 to 2, not the entire parabola. So from -1 to 2. So a rough sketch of this graph, that 3 would make it open a little steeper. It looks something like this on that interval. So we can see the average value, in this case we found it's -2 because you can see more of the graph is below the x-axis than above it. So that's why we have a negative average value. So you can have a negative average value. That is possible. If more of the graph is below the x-axis than above. All right, now let's take a look at where we have the graph of f instead of the equation for it. So the graph of f is shown below. Find that, again, there's the average value of f of x on the interval -8 to 6. So this time that's our a and b values. So again, you start off with 1 over b minus a, in this case 6 minus -8, times the integral from -8 to 6 of whatever you're finding the average of, in this case the function f of x. So that simplifies to be 1 over 14. And this time we don't have the equation for this, so you just have to remember what the definite integral represents graphically. Well, graphically, remember, it's just the area between the curve and the x-axis. So we're going from -8, which is at the very end of our graph here, all the way to 6, which isn't quite to the end, stopping right there. And these are just made of geometric shapes, you can see, so we can just find the area of those. So let's split it right here. See, we've got the square. The area of the square, it's 2 times base is 2, height is 2. So it's 4, but it's below the x-axis, so it's -4. Then we've got this triangle, 1/2, the base is 2, the height is 2. So we get 2, but it's negative below the x-axis. Then notice we've got this quarter circle here. So it's 1/4 of a circle, 1/4 pi radius squared. And you can see the radius, if this was a whole circle, you can see the center would be right here. So the radius is 1, 2, 3, 4, 1, 2, 3, 4, so the radius is 4. So that would be 16, 4 squared, times 1/4. Well, 16 divided by 4 is 4, so this gives you 4 pi. And it's positive because it's above the x-axis. Then if we split it right here, we can split this one. You can use the trapezoid formula if you remember that. Or we can just split it into a rectangle and a triangle here. The rectangle is 3 by 2, so it's 6. The triangle is 1/2 3 by 2, so that's 3. So altogether that's 9. Then we have this little triangle right here. 1/2, the base is 1. The height is 2, so the 2's reduced out, you just get 1. And then finally, this little triangle here, 1/2 the base is 2, the height is 3, so that gives you 3, but it's negative. So what that definite integral represents is all those areas added up. So negative 4 minus 2 plus 4 pi plus 3 plus 6 plus 1 minus 3. And the whole thing times the 1/14. So you get 1/14. Now let's see what that simplifies to be. Well, we definitely have 4 pi. And then let's combine the constants here. You can see the 4 and the negative, the 4 and the negative 2 give you negative 6. That cancels out with a 6. So then we have 3 minus 3. Those cancel out, so all that's left is 1. So 4 pi plus 1. So you could leave it like that, or if you just make it a single fraction, you can see that would be 4 pi plus 1 over 14. It's our average value of it. So let's see if this seems reasonable here for an average value in the function on the interval. Well, 4 times pi, if we round pi up to 3, that's around a little more than 12, plus 1, a little more than 13. So a little more than 13 14ths, that's a little bit less than 1. So it's saying the average value is a little less than 1 on the interval. And see how that cuts through towards the middle of the graph there? So that is a reasonable average value, isn't it, for our average y value. If we got an average value like way down here, yeah, that's probably not going to make sense, right? Because it's not really the middle of the graph, or way up here somewhere. So you can see on these graph ones if your answer is reasonable or not. All right, let's take a look at a multiple choice type of question. It says on the closed interval from 1 to 5, which of the following could be the graph of the function f with the property that this is true? Well, first, you just need to recognize what this represents. You've got 1 over, there's your b minus a, integral from a to b of this function. So you have to first recognize, okay, this means the average value of f of x on the interval from 1 to 5. That's what that is. So just come right from it. And it's telling you that average value is 2. So let's look at our choices. Well, if we think about 2 here, 2, all right. Well, there's no way this average value is 2, right? You can see the average value of this one is 3, it just stays at 3 the whole time. So yeah, that can't be it. Let's take a look at our other ones. All the other ones, 2 is kind of in the middle of the graph somewhere. So to see which one it is, what you can do is let's simplify this. This simplifies it would just be 1/4 out in front, 5 minus 1. And then the integral from 1 to 5 of f of 2 would be. And we know that has to equal 2. So I think the easiest way to do this is to try to isolate this definite integral. In other words, let's get rid of that 1/4 by multiplying both sides of the equation by 4. And then we'll just have the definite integral isolated, integral from 1 to 5 of f of t dt would equal 2 times 4, 8. And remember what the definite integral represents here is the exact area under the curve from 1 to 5. So we want that area to be exactly 8. So now we have something we can work with. Well, unfortunately these curves though, we don't have the equation for them, so it's going to be hard to get the exact area. So let's try to see what it could be based on the closest geometric shape that somewhat follows this curve. In this case, you can see this is kind of like a triangle, but it's not exactly a triangle, right? So if we draw that triangle in here, let's see, well, at least we could find the area of that triangle, couldn't we? So the area of that triangle would be 1/2, the base you can see is 1, 2, 3, 4. The height is 1, 2, 3, 4. So that area of that triangle is actually exactly 8. Well, if the triangle is exactly 8, that means this curve is too big, right? You can see that has an area greater than 8. So that can't be it. And if you use that same triangle on B with a curve there, you can see again the area is 8. But this time that is too small, isn't it? So that's less than 8 definitely. So those can't be it for sure. Then we have two other ones that are just geometric shapes. So let's check this one out. Well, if we divide this into a rectangle and a triangle, the rectangle is 1 by 4. So that's an area of 4, and the triangle is 1/2. The base is 4, the height is 3, so that's 6. You can see overall that's 10, that's too big, so that can't be it. And then if you look at this last one here, remember it's the area between the curve and the x-axis, so it's not this goes on forever. It's these that are between the curve and the x of these two triangles here. So it'd be 1/2, one of these triangles, the base is 2, the height is 4. So that would give you 4, and this has the same area of 4, so you can see that one does equal exactly 8, so that would be our answer. All right, let's take a look at one with a table of values. So it gives you the table of values of function f, a twice differentiable function in its first and second derivative. So here's f prime and f double prime. And it says, what's the average rate of change of f over the interval -2 to 3, or a to b. So first thing we need with average, 1 over b minus a. In this case, 3 minus -2. And then the integral from -2 to 3 of whatever we're trying to find the average of. But read it carefully. Not the average of f, it's the average rate of change of f. That means the derivative of f prime. So that's what we're finding the average of, so that's what's going to go inside of our integral. That's f prime is what we're finding the average. So on the outside, that simplifies to be 1/5. And just think, when you integrate f prime, well, find the antiderivative, wouldn't that give you back the original function, f of x? Evaluated from -2 to 3. So we have 1/5 on the outside. Then you substitute in the upper limit, so that'd be f of 3 minus f of -2. And finally, here's where we can utilize the table to help us out. Looking at the table, we can see f of 3. Well, when x is 3, f is 0. So that's 0. Minus f of -2. When x is -2, f is 7. So that'd be -7 times 1/5, so we get -7/5. And now let's find the average rate of change of f prime. The interval is slightly different, so average again. But it says the rate of change of f prime. Well, that means the derivative of f prime, which is f double prime. So that's what we're finding the average of here, the second derivative. And the interval is, in this case, from a to b is -2 to 4. So again, since we're finding the average, you'd start off with 1 over b minus a, 1 over 4 minus -2, times the integral from -2 to 4 of whatever we're finding the average of. In this case, we're finding the average of f double prime, the rate of change of f prime. And so then we've got 1/6 on the outside. When you integrate f double prime, well, that gives you back the first derivative when you find the antiderivative, doesn't it? Back to f prime of x. Evaluated from -2 to 4. So we have 1/6. And then we can substitute in the upper limit 4, so that's f prime of 4 minus, let's substitute in the lower limit of -2, f prime of -2. And again, now we can refer back to our table here. You can see f prime of 4, when x is 4, f prime is 2, minus f prime of -2, when x is -2, f prime is 0. So we get 2 times 1/6, 2/6 reduces to 1/3. So that's the average value of the rate of change of f prime, and with f double prime on the interval -2 to 4. All right, now let's take a look at an application with position, velocity, and acceleration. So it says the velocity of an object traveling in a straight line is given by this. So here's our velocity function. And we want to find the average velocity on the time interval from 0 to 3. So in this case, again, it's average. So we start off with 1 over, there's our b minus a, 3 minus 0 is our interval, times the integral from 0 to 3 of, well, what do we find the average of? In this case, it's the average velocity. So v of t would go here, which we have right here. So sine pi t over 2, and then times dt. So we just have 1/3 on the outside. But in order to integrate this, notice we have a function inside, so this one is going to require u substitution. So you'd say u equal to pi t over 2, but if you write it that way, it's going to look like you have to use the quotient rule, which you could, but it's probably easier if you just pull the constant pi over 2 out in the front times t, so you can see you actually don't need the quotient rule. However, since this is a definite integral and we're using u substitution, what we do have to do is convert our lower and upper limits. So when you substitute in 3, that becomes 3 times pi over 2, 3 pi over 2. And when you substitute in 0, it wipes that out, so it just stays 0. And then we've got the sine of u, but again, to get rid of dt, we have to take the derivative of what we set u equal to. So in this case, du dt is pi over 2. And then if you cross multiply, you get pi dt equals 2 du. Solve for dt, divide by pi, so dt equals 2 du over pi. I can substitute that in for the dt right here. Then we can pull the constant 2 over pi out in front times the 1/3 will give you 2 over 3 pi. And then when you integrate sine, that's all that's left, you get negative cosine. That negative we can pull out in front, so we don't have to deal with it outside. That's a constant, along with the 2 over 3 pi. And then it's just evaluated from 0 to 3 pi over 2. So we've got negative 2 over 3 pi. And then when you plug in 3 pi over 2, cosine of 3 pi over 2, minus, plug in 0, cosine of 0. So negative 2 over 3 pi. Then we have to evaluate cosine of 3 pi over 2. Well, 3 pi over 2 is right there. Cosine is the x-coordinate, which is 0. Minus cosine of 0, right there, is the x-coordinate, which is 1. Whoops. So we get negative 1 times negative 2 over 3 pi gives you positive 2 over 3 pi. And notice for velocity, we're not giving you units on this one, so don't have to put units there, so just 2 over 3 pi. Now let's take a look at part B. It says what's the average again, but this time it's the average acceleration. On the same interval though, from 0 to 3. So for average, again, we'd still start off with 1 over b minus a, 3 minus 0. We'd still have the integral from 0 to 3. But this time we wanted to find the average of its acceleration, not velocity. So we could write this as a of t or v prime of t right here. And now there's a couple different ways we could go about this. We could find the acceleration function. Remember, to go from velocity to acceleration, we take the derivative. So we could just take the derivative of this using the chain rule. And then once we get that, put that back in here, and then we'd have something to integrate. However, there's actually an easier way to go about it. You just think about this logically here. We've got 1/3 on the outside. And if you integrate acceleration, well, isn't that going to give you back velocity? So we can say v of t. And we already have velocity right there. So there's no need to figure out the acceleration, because when you integrate it, it goes back to velocity anyway. So we've got 1/3 on the outside. Then you substitute in the 3. It'd be v of 3 minus substitute 0, v of 0. So now we just need to find v of 3 and v of 0. We can do that because we have the velocity function right here. So v of 3, when you plug in 3 for t, that becomes the sine of 3 pi over 2, which you can see right here is negative 1, the y-coordinate. So we have 1/3. I just figured out v of 3 is negative 1. And minus v of 0. So So b of 0 would be the sine of 0, which is the y-coordinate, which is 0. So that's negative 1 minus 0. So we get negative 1 times 1/3 gives you negative 1/3. Again, we don't have any units on it. Now let's take a look at another topic in addition to average. So another topic we're going to look at is integration of odd and even functions. So remember, an even function, like this one, means it's symmetrical about the y-axis. So the y-axis here is symmetrical about that. And an odd function is symmetrical about the origin. See, this is symmetrical about the origin. Notice we don't have a name for a function symmetrical about the x-axis. That's because if it was symmetrical about the x-axis, like a sideways parabola here, it's not going to pass the vertical line test. It won't be a function. And just remember, odd and origin both start with O. That's an easy way to remember that one goes with that. So let's see their properties with the definite integrals. This says from negative a to a. So to make this simpler, I'm just going to make negative a negative 4 and a 4. So I can see exactly what it is. It really could be any one that are opposites. This is saying the integral from negative a to a, if it's an even function like this, is the same as twice the integral from 0 to a. And you can see why that is because of the symmetry. Isn't that area going to be exactly the same as that area? So you can just double it from 0 to a and you get the same thing. Whereas if it's an odd function from negative a to a, again, to make this simpler, let's just make it negative 4 to 4. Or let's go negative 6 to 6, I guess. There's negative a. There's a. This time, if you integrate from negative a to it's an odd function, you can see one's above the x-axis, one's below, and they're the same area, so they're going to completely cancel out, leaving you with 0. It's an odd function. So let's take a look at some definite integral problems involving even and odd functions. Similar to the ones we did earlier, except those we didn't know if they were even or odd. So we're told f of x is an even function, and we're given the definite integral from 0 to 3 of f of x dx is negative 4. So remember to organize our information here. Let's draw our number line. So from 0 to 3, and we're told that definite integral is negative 4. I'll put a little brace here, represent and below since it's negative, negative 4. But remember, this is an even function. So since it's even, remember this is where your y-axis would be right at 0. That means, before we even look at the other one, we know another integral as well from negative 3 to 0 has to be the same as this, right? Because of the symmetry. So this would also have to be negative 4. And then the second one we're given is from negative 7 to 0, the definite integral equals 6. So negative 7 right here to 0, that's equal to 6. Well, if that's equal to 6, then we know, because of the symmetry, it's even from 0 to 7, that would also have to equal 6. And then before we start answering the questions there, remember, if you can figure out what all the smaller intervals are on your number line, you'll be able to answer any question they can ask, because you can always add up the small ones so you get the larger ones. So, from 3 to 7, what would that have to be? Well, two ways of thinking about it. One way is think negative 4 plus this would have to equal 6. So negative 4 plus what number would give you a positive 6? Well, that would be 10, wouldn't it? That's one way to think about it. Or the other way you can think about it is you can take the bigger interval, 6, and subtract the smaller one, negative 4. 6 minus negative 4 becomes 6 plus 4, which is 10. So either way works, whichever is easier for you to think about. And if that one's 10, because it's even, we know the other side from negative 7 to negative 3 would also have to be 10. All right, now let's start answering all the questions they have below these definite intervals. Negative 3 to 0, we can see we figured out that one is negative 4. Negative 7 to negative 3, we already figured out that one is positive 10. This one, we've got a couple things going on here, a little different. Notice we've got a 2 we can pull on the outside, the constant. And these are in the wrong order, aren't they? So that's going to make it the opposite sign when we flip it. It really should be normally written as from 3 to 7 instead of 7 to 3. X dx. And then we've got negative 2 on the outside. And we can see from our number line from 3 to 7, it's positive 10. But here it gets multiplied by negative 2, giving you negative 20. And finally on this one, let's look at one where we have f of x plus 2. Well, remember, when you have things added or subtracted, they can be integrated separately. And on this one, it's actually helpful to separate them into 2 separate integrals. So from negative 7 to 7, f of x dx plus the integral from negative 7 to 7 of just 2. So negative 7 to 7 of f of x. Well, negative 7 to 7, different ways to get that, but you can add up the small ones. You could have all these little ones, but you could easier to just add 6 plus 6. So, and then this one is just a simple integral. When you integrate 2, you get 2x evaluated from negative 7 to 7. So that gives you 12, using our number line there, plus, when you substitute in 7, you get 7 times 2. You could pull out the 2 here, but it's probably just as simple to just plug it in right now. 2 times 7, 14. Minus, when you plug in negative 7, you get negative 14. So you can see that's 12 plus 14, that becomes plus 14 is 28. Gives you 40. All right, now let's take a look at an odd function. So it says this time f of x is an odd function, symmetrical about the origin. And again, let's use our number line to organize the information. So we know here, from negative 4 to 0, the definite integral is 6. So we put 0 here, negative 4, and we know that's a positive 6. But because it's odd, that's symmetrical about the origins, so automatically that means from 0 to 4, since this is positive 6, over here this would have to be the opposite of negative 6. And then the other one we're told is from 8 to negative 4, but notice those are in the wrong order, because that one's 3. So that means if you were to flip it from negative 4 to 8, that would actually equal negative 3. So we've already got negative 4 on there. Let's put 8 on there. So that means from negative 4 all the way to 8, that whole thing is negative 3. So this one, when it crosses over 0, it's kind of harder to flip it around like we've done the other ones with the symmetry. So what I would do instead is just work on this little interval, what this has to be from 4 to 8. Well, remember these little intervals have to add up to be the big ones. They have to add up to be negative 3. Well, 6 and negative 6 already add up to be 0, so that means the 4 to 8 would have to be negative 3 in order for all 3 of them to add up to be negative 3. And then based on the symmetry, the little interval is easier to mirror. That means since 4 to 8 is negative 3 and it's an odd function, it'd have to be the opposite from negative 8 to 4 would have to be a positive 3. Now we've got all the little intervals on our number line, so we're able to figure out anything they could ask us. So from 0 to 4, we can see that's negative 6. From negative 8 to negative 4, we figured out that's 3. From negative 11 to 11, well, that's not on our number line. But remember, it's an odd function, right? And if these are the opposite, remember the property right here, negative 8, 8, that's always going to be 0. So the opposite numbers. So we didn't need the number line at all on that one. Just the fact that it's odd. This could have been negative 11 billion to positive 11 billion, still be 0. As long as they're the opposite and it's an odd function. And then the last one, Notice again we've got a minus here, so we can integrate these separately. And this first one also has a 2 out in front, so that can be pulled out as a constant. So it'd be 2. This is the first one though, times the integral from 0 to 8 of f of x dx. This time though it's minus the integral from 0 to 8 of x. So we've got 2 times, well we can see from 0 to 8, well that would require adding up these two, negative 6 and negative 3. And then minus, this is just a nice simple integral you can integrate by hand. When you integrate x, you get x squared over 2, evaluated from 0 to 8. So this is negative 9 times 2, so that's negative 18. Minus, when you substitute in the 8 first, 8 squared is 64, divided by 2 is 32. Minus, when you substitute in 0, that's just 0. So 32 minus 0. So that's negative 18 minus 32 gives you negative 50. That's what that definite equation is. And that concludes the notes for AP Calculus on the topic of the average value of a function on an interval, as well as even and odd function properties for definite intervals.